We're continuing our discussion of the problem on determining the masses of stars. And remember, we have a binary system. These stars are moving in a circular orbit around the center of mass, and they have identical masses. And we are trying to measure the masses of these stars from the Earth. And we also have the plane of the star's orbit being edge on with the line of sight of an observer on Earth. And in the first part of the problem, we have gone through relativistic Doppler shift formulas and we have derived those. Now we're going to proceed with part A. The light produced by heated hydrogen gas in a laboratory on Earth has a frequency f0 of 4.568110 10 to 14 Hz. In the light received from the stars by a telescope on the Earth, hydrogen light is observed to vary in frequency between 4.56771 times 10 to 14 Hz and 4.56891 times 10 to 14 Hz. Determine whether the binary star system as a whole is moving toward or away from the Earth, the speed of this motion, and the orbital speeds of the stars. And there's a hint, the speeds involved are much less than c. Actually, normally we don't need the relativistic Doppler formulas, but we're going to go ahead and use these anyway. Okay, so we found that for the source moving toward the observer, the detected frequency is the original frequency multiplied by square root c plus u divided by square root c minus u. And for the source moving away from the observer, it is square root c minus u divided by square root c plus u times f0. And here we had a stationary observer and the source is moving towards the observer with speed u. Now looking at the given values in the problem, in the S frame, when you measure the heated hydrogen gas spectrum, we find a frequency of 4.56811 10 to 14 Hz. There is a minimum frequency measured on Earth and the maximum frequency measured on Earth for the light that is coming from these stars. And let's say that the top star is moving with a tangential speed v and the bottom star is moving with a tangential speed v on this circular orbit. And as a whole, this system has a velocity of the center of mass that is directed away from the Earth observer in this convention. Now, we see that the source of the light is approaching the observer for the top star. And with what speed is it approaching? It is its tangential speed v minus the speed of the center of mass, and it's moving away from the observer for the bottom star, and it's moving away with tangential speed v plus speed of the center of mass, v plus v center of mass. Okay, so we can use our relativistic Doppler shift formulas. For the maximum frequency detected, it is the actual frequency f0 times square root c plus u. Now, u is the relative speed of the source of the light with respect to the stationary observer. Here, we have for the top star that is approaching with a relative speed v minus v center of mass. So it is c plus v minus v center of mass square root divided by c minus v plus v center of mass square root. So remember that we had for the source moving toward the observer, approaching the observer, square root c plus u over square root c minus u. Here u is v minus v center of mass, and for this case u will be v plus v center of mass. Okay, so the frequency is increasing because it's C plus U on top and C minus U at the bottom. So that will give us the maximum frequency. Now, if I call the ratio of the maximum frequency squared to the original frequency squared, F max squared divided by F0 squared, I can see that this ratio is C plus V minus V center of mass divided by C minus V plus V center of mass. So if I multiply the bottom with A and equate it to the top, I will obtain AC minus AV plus AV center of mass is equal to C plus V minus V center of mass. So I can write this in V parentheses. It's V times A plus 1. And then I have minus V center of mass parentheses. It is in minus V center of parentheses, I will have A plus 1 on the right hand side. A plus 1. And this is equal to, if I take C to the left hand side, A times C times A minus 1. A minus 1 times C. So V minus V center of mass can then be written as A minus 1 divided by A plus 1 multiplied by C. Okay, so let's call this the star equation. Now, if the source is moving away, we have to deal with the minimum frequency. The minimum frequency is F0 times C minus V minus V center of mass divided by C plus V center of mass. Because that is this scenario, source moving away with a speed V plus V center of mass. We have the square root on top and square root at the bottom. And now I call B the ratio of minimum frequency squared to F0 squared, which is equal to C minus V center of mass divided by C plus V center of mass, and multiplying the bottom with B, equating it to the top, I have BC plus BV plus BV center of mass is equal to C minus V center of mass. That gives me, in V parentheses, if I take it to the left hand side, V times B plus 1. And if I take this one to the left hand side, plus V center of mass times B plus 1 is equal to, I take BC to the right hand side, I have 1 minus B multiplied by C. So dividing both sides with B plus 1, I will obtain V plus V center of mass is equal to 1 minus B over 1 plus b times c. So let's call this double star equation. Okay. Now if I add these two equations, star equation and double star equation, I will have v minus v center of mass plus v center of mass. So v minus v center of mass plus v center of mass. This is equal to a minus 1 over a plus 1, a minus 1 over a plus 1, plus 1 minus b over 1 plus b, multiplied by c. And v center of masses will disappear. They will cancel out. And I will obtain the tangential speed of the stars to be v is equal to c over 2 a minus 1 over a plus 1 plus 1 minus b over 1 plus b, where a is f max squared over f0 squared, and b is f min squared over f0 squared. Now let's plug in the numbers. We have for a maximum frequency 4.56891. So 4.56810. And for f0 we have 4.5681110. And I'm going to take the square of the top and square of the bottom. That gives us for a 1.00035028493. And I do the same for b. This time I have minimum frequency square. Minimum frequency is here. 4.56710 squared divided by 4.568110 squared, and that gives us 0.9998248800536. So if I plug in these to this equation for a and b, and take c to be 3 times 10 to 8 meters per second, I can find v, the tangential speed, to be 3.94 times 10 to 4 meters per second. And what I was asked to find was velocity of the center of mass. The center of mass velocity is 1 minus b over 1 plus b times c, the double star equation, minus v. And this gives us, for the velocity of the center of mass, minus 13.1 times 10 to 4 meters per second. Now notice that the center of mass velocity turned out to be negative. So since V center of mass is negative, we can reach the conclusion the binary star is approaching the Earth. Okay. So we were asked to determine whether the binary star system as a whole is moving toward or away from the Earth, and we found that it's moving toward the Earth. We found the speed of this motion and the orbital speed of the stars. The orbital speed is 3.94 10 to 4 meters per second. The velocity of the center of mass is minus 13.1 10 to 4 meters per second. The minus sign indicates that it's approaching the Earth.